all the things I said on Tuesday don't change. We want to try and get to our position where we don't have any homework over the Thanksgiving break. So I figured you guys would appreciate that we just get right on into it. So I'm going to switch on over here and get started. We were talking about circular motion on Friday. And so I kind of want to finish that discussion. And then if we have a chance, maybe take a moment and talk a little bit about some of your homework questions so you kind of get an idea for what to expect in the homework as well. So how many of you have gotten started on the homework? Just give me a quick show of hands. Is it in line with what we've been talking about in class? It shouldn't be all that different. There's basically 4 or 5 kinds of questions related to this. We did 3 of them or so in class. And so the roller coaster, when it's on the top of the track, you're looking for that minimum, the car going over the hill, looking for that, the max speed you can drive. Those are pretty typical questions. There's a variety of questions that are similar to that sound like they're a little different, but they're really the same question. They tend to have things like, how fast can you spin something when it's attached to a string, if the string has like a maximum tension that it can withstand. So it's the same kind of question. The only difference is that the normal force is being replaced with the tension force. It's the tension that actually causes the object to travel in a circular path. But I want to talk about this question because this is also very typical, and it's the space station question. So we're going to talk a little bit more about centripetal motion, and then we're going to talk for a few minutes about gravity. So the space station questions tend to revolve around the idea that you could create a space station where people could walk with what's called simulated gravity. So the idea of simulated gravity tends to begin with a fictionalized space station, something that may look like this. Circular, and it's spinning, at least in all the movies it is. Or it's a section of the spaceship that's spinning. So like if you've seen The Martian, they have a big section of the spaceship that's spinning, and they're exercising in there, and they have all the places where they sit down or in there. That's because that section that's spinning has what's called simulated gravity. It's centripetal gravity. The idea is that the people are actually walking on the inside edge, kind of like that. They don't actually experience gravity. What they experience is their own inertia, and the floor of the space station provides a normal force that simulates the normal force they would experience on the Earth. So in a space station like this, a person that's standing on the edge there, their body would want to travel, with this tangential velocity. And their inertia would have them travel right along that straight line. But the issue is that they're going to encounter the wall of the space station. And the wall of the space station is going to provide a normal force in this direction. This normal force is what gives them a sense of gravity. It's not really gravity. It's just providing them the normal force they would normally experience if they were on, a planet. The truth is their inertia is flinging them towards the edge of the space station. And it is the space station that's keeping them from flying out into space that simulates this idea of gravity. This kind of problem is pretty straightforward in that we're still dealing with a net force equals ma kind of problem. The difference here, of course, is that they're not speeding up or slowing down. That a is the centripetal acceleration. And generally, these kinds of problems are attempting to give us a sense of gravity from a unbalanced normal force. So if we wanted to simulate gravity, we'd have to simulate how much normal force you would normally experience on the Earth. So if you wanted the space station to spin in such a way that it felt just like the Earth, we'd replace that normal force with what you would want to experience, your weight. Now, what makes these problems generally a little different than what you're used to is they tend to not be in terms of how fast you're actually moving inside the space station. Instead, they tend to be in terms of the angular velocity. of the space station. What I mean by that is we don't really talk about how fast you're going here. We talk about how fast the space station spins. This is what we talked about when we first started talking about rotational motion a couple of days ago. So what we'd like to talk about for the next few minutes is the relationship between the linear velocity that a person has on a space station like this and the angular velocity of the space station. That little W is the lowercase Greek letter omega that is typically used for angular velocity. And I draw it like that, but it kind of looks, it just looks like a W, but it stands for angular velocity. And it's measured in things like RPM, which is rotations per minute. But also it can be measured in radians per second or radians per minute. Angular velocity is just another way of measuring how fast something is spinning. And the difference is that angular velocity is the same every place on the space station, while linear velocity is different depending on where on the space station you are. So if the person was actually standing, say, here on the space station, because their radius is smaller than the radius of the person out here, these two people have two different linear velocities, but they have the same angular velocity. I just realized I wrote all that stuff underneath my head, meaning you guys can't see it. So there you go. So what I'd like to talk about just real quick is transitioning between angular velocity and linear velocity. So one of the easiest ways to talk about this is something that all of us kind of have a shared experience about, and that's probably riding like a carousel when we were kids, you know, the ones with the horses on it. So I want you to imagine a carousel that might have 3 horses on it. So maybe you and your siblings all on the 3 horses. Now, if you're like me and you put your kids on the carousel, you don't necessarily have to ride it yourself because you can just sit out and watch them ride it. So you might be able to determine the angular speed of the carousel just by counting how long it takes between when you see them and when you see them again. So if the whole thing is spinning, it might take 4 seconds between when they pass you once and they pass you again. So it's not uncommon for me to say that the angular speed of a ride like this is 1 rotation every 4 seconds. That's an angular speed the way it's presented. 1 rotation every 4 seconds. So if you've been doing any of your homework and you've come across a problem like this, they're telling you the angular speed when they say 1 rotation every 4 seconds. I know there's questions in the homework about like the Earth and the moon, the idea that the Earth's angular velocity can pretty easily be expressed. You could just say it's 1 rotation every 24 hours. That's the angular speed of the Earth. That doesn't tell you how fast you're going, but it tells you how fast the Earth is spinning. It's giving you the number of rotations it takes and how long it takes to make those rotations. So I could actually write this as 0.25 rotations per second. And that would be the unit of the angular velocity of the merry-go-round. The first thing you have to know about converting from angular velocity to linear velocity is that it can only be done so in radians. So if you're going to take any notes today about this, right now you should highlight that everything has to be converted to radians first when you're going to convert from angular to linear. We will eventually have to convert everything from angular to linear and back later in the year, so we better get used to it now. Converting from angular to linear isn't hard, but some of you still have trouble with the idea of radians. It's not too big a deal. All you have to remember, if you want to remember how to do this, is the equation for circumference, because it is converting. 2 pi is the angular measurement, and c is the linear measurement, the circumference. That is the conversion from angular to linear. It just reminds you that you have to be in radians because 2 pi should be a good reminder of the number of radians it takes to rotate once. So if I want to convert my 0.25 rotations per second into radians per second, I have to use a unit multiplier that gives me my 2 pi radians for every one rotation. And remember, you're really just multiplying by a number that's about 6. So when doing this, let's be careful that we don't make silly mistakes, because it's really easy to make silly mistakes here. And I'm going to describe a silly mistake here in just a minute, so have your calculators ready. If you don't have them in front of you, let's go grab one real quick. And I'd encourage you to use the calculator you're going to use on your next test, not your phone calculator. Now, I'll ask real quick, because this one's pretty straightforward. Somebody give me my angular speed here in radians per second. Mr. Shelton waits patiently.
Is it 1.57?
Sounds about right. So generally, I'm supposed to tell you that radians are unitless, but I would really encourage you to just write out something to remind you that that number's in radians. So I put radians up there, just rad, something like that. Now, converting from linear to angular or angular to linear is pretty easy. You just multiply by the radius. So the linear speed of any object is the angular speed times how far away from the center they are. This is the conversion that converts from linear to angular. You're just multiplying by the radius or dividing by the radius. So in this example with um, the carousel horses, different kids on the carousel are traveling at definitely different speeds, because the ones that are further away from the center are going to be traveling faster than the ones that are inside. That's why the rules have always been to put the little kids on the inside horses and the bigger kids on the outside horses. They want the little kids on the safer horses, the ones that aren't moving very much. And you can put the bigger kids on the outside horses. David threw something up in the chat, and I'm going to be honest with you guys. I'm not checking the chat very much, but his question is, can you leave it with the pi in the expression? Generally, for most of what we're going to do, that should be fine. But if you're asked for a numerical answer, they're going to want you to go ahead and put pi in. All right. So I'd like you to put pi in when we do it today, mostly so you can make the comparisons that we're going to need to have. But I don't want to belabor it too much. I don't want to spend a lot of time on this. This conversion is no big deal. And if you struggle with it, get over yourself. It's not hard to do. I need you to recognize that when we're calculating the centripetal acceleration, which is why we're talking about this at all, when you're calculating that centripetal acceleration, it tends to be in terms of the linear speed. So if you have angular speed and you're asked to calculate the centripetal acceleration, you probably will have to convert it into the angular speed first. Convert into the linear speed first, and then you can use this. Of course, if you're savvy, and some of you are, you realize that you could probably just substitute and come up with a different way of calculating the centripetal acceleration, one that's not in terms of the angular speed, but in terms of one that is in terms of the angular speed and not the linear speed. I'll move my head out of the way. So what I mean by that is, if you put in omega times r here and simplify it down, you get a different way of calculating the centripetal acceleration in terms of that angular speed. I would, if I were you, know both of these. It's on the equation sheet. So you don't have to memorize it, but you might want to start highlighting things on your equation sheet to make them easier to find, especially things that are more relevant for each test. So for your next test, which is going to have this kind of stuff in it, I would find on the equation sheet where the angular stuff is and just highlight all of it real quick. That way you can find it quick. There's a lot of stuff in that sheet that's not useful, that you're never going to use or you're not going to use anytime real soon. So for the time being, rather being this daunting thing where you're trying to search it all the time, why don't you just go ahead and make it pretty clear to yourself which things are the most important right now. You can't add anything to the sheet. I want the sheets to be the same sheets you're going to have in the exam. But there's absolutely nothing wrong with right now drawing your attention to the important parts that you're studying. You need to save time on the test, and this is one way to do so. So what I'd like to ask is, real quick, if we actually had this particular ride, and this was the angular speed of the ride, then if I tell you that the three of you are all on a ride, and the inner kid is 2 meters from the center, the middle kid is 4 meters from the center, and the outer kid is 6 meters from the center, you should be able to pretty easily figure out which kid is going to have a lot more acceleration than the others. It's pretty straightforward because it's just based on how far away they are from the center. They all have the same angular speed, but the kid on the outside being 3 times farther away than the kid on the inside, he's going to experience 3 times the acceleration. What that really means is he has to hold on with 3 times more force than the kid that's on the inside. This acceleration, remember, requires a force. And if you've ever ridden one of these horses, you feel like you're being thrown off the ride. It's not terrible. It's pretty gentle. That's why it's for little kids. But how many of you have ridden one of these rides at the adult version of this ride? They have them tend to be at like they tend to be at like the fair and stuff. It looks something like this. And then you're kind of stuck up here on this edge of the ride. You ever seen these where you're kind of flung up against the edge of the ride and they spin around and you feel like you're stuck to the edge? That's the adult version of the merry-go-rounds you used to ride when you were kids, where you're on the horse. This is just taking it up a notch, where it spins you fast enough where you feel like you're pinned up against the wall. How many of you have been to the one that's like all enclosed and the floor drops out and you're stuck on the wall? Any of you guys ever ridden one of those? They're not great anymore. And a lot of parks don't have them because they're more like big vomit fests, if you think about it. You go in there, eat a whole bunch of that crappy kind of carnival food, and then they spin you around really fast for a while. That's why the inside of them tends to be, indoor, outdoor carpet, because it's easy to hose off after somebody kind of loses their carnival food all over it. But this kind of ride is pretty common. You figure the person that's on the ride, if they get actually stuck to the edge, there's an upward frictional force that holds them in place against the gravity, which is acting downwards. And the thing that is causing the centripetal force is a normal force from the wall. If you spin it fast enough, you should be able to create enough friction where you'll be able to be suspended against the wall. And that's what these rides do. So we're going to do one more thing, and then we're going to start talking about gravity. And it's to try and emphasize what we just talked about a moment ago. We're going to talk about you standing on you standing on the edge of the earth. I want you first, before we do anything else, to figure out how fast you're traveling when you're standing on the equator of the earth. It sounds like a weird question, but it's based on what we just talked about. In order to know the answer to this question, you're going to need the radius of the earth. The radius of the earth is 6.37 times 10 to the 6th meters. Now, think you have everything else you need, all you need to do is tell me how fast are you moving when you're standing on the edge of the earth if you're on the circumference. And don't leave it in terms of pi. I'd like it in terms of meters per second. Now, if you don't know what I'm asking, start here. That's where you should start. I gave you this. You have to bring me this. I'll help you. It's not hard. The Earth goes around once every 24 hours. But you're going to need to convert that to radians per second. So if you know what I'm asking you to do, please get it done. If you don't know what I'm asking you to do, then please say no in the participant window. No, I don't know what you're asking me to do. So weird talking about physics without wearing a mask. I feel so naked and exposed. I brought everything home. My green screen, my microphones, my lights. It's all here. I was afraid I wouldn't feel like I was at school if I didn't have my school stuff. Also, because they're opening it up as a shelter, I figured somebody'd walk off with it or use my green screen as a blanket. We don't want that. Hopefully, you're getting to a point where we're almost done. If you think you have a number, go ahead and put that number in the chat. It should be in meters per second. For the first time, I'll actually look at the chat. And I'll tell you if you're right or wrong. Wow, nobody. There's one. Boyd has an answer. I'm not going to tell all of you if it's right or wrong. I'm just going to tell Boyd if it's right or wrong. And Trevor's got an answer. Oh, David's got an answer. I think. Do you think he actually came up with it himself, or he just copied Boyd's answer? I don't know. I think we can trust David. He tends to be all right. He really likes his hair, though. If you guys noticed, he's adjusted it many times during the starter class. The problem with Zoom school is how much everybody's focused on their own hair. Because it's right there in front of you the whole time. I know. Anybody else going to offer? It's only 3 people. Jacob thinks he has it too. Seeing a lot of the same answer. So if you haven't figured it out yet, it is 463 meters per second. Now, if you need help getting that number, you probably should speak up. Otherwise, I'm going to assume that you guys can do these kind of big conversions and deal with the numbers and the fractions and all that. Remember earlier in the week, I asked if you're going to need help when it comes to dealing with converting from one number to another. You guys said you needed to maybe have a quick refresher. That was your refresher. If that's not enough, don't keep it a secret.
Mr. Shelton, can you show us how to get that?
I'll be happy to show you guys how to get this, okay? I'm going to start by converting my angular speed into radians per second, I know that the Earth's angular speed is 1 rotation every 24 hours. I use unit multipliers for converting. And although they're no fun, they tend to be pretty time consuming. They work, and they tend to be clear enough that you can kind of see what you're doing a little at a time. So I'm sorry, I'm getting a question in the chat, and I'm going to answer it real fast, and it's private, so shh, don't tell anybody, it's a secret. So you have to pick some place to start. Like, you either have to start by converting the rotations or start by converting the time. You need to pick. It doesn't matter which thing you start with. So I'm going to start by converting the rotations into radians. So you put what you need in the spot where you need to have it. For example, I need radians here. I need the top to be radians. And I want to get rid of rotations. So I put it on the opposite side. I can do this in one conversion, so it's pretty easy. And then you need to put your unit conversion in here, knowing that for every 1 rotation, there's 2 pi radians. So that's a unit converter, and I'm using multipliers to do so. So the next thing I need to do is I need to get rid of the hours. But, if you don't know, the direct conversion from hours to seconds, you might have to dance it through minutes first. So, and that's what I'm going to do. I'm going to do it the long way so that you don't have to carry a lot of stuff with you. I'll put hours on top because I want to cancel hours. I'm going to put minutes on the bottom. And then I'm going to put my conversion fact in here that for every 1 hour, there's 60 minutes. And this gets me closer because now as I start canceling these things out, I have radians per minute, but I'm still not where I need to be. I need radians per second. So I'm going to need to get rid of the minutes. Give me seconds. I need my conversion fact here too for every 1 minute, 60 seconds. And now it looks like if I read this correctly, I will be left with radians per second. So this is the conversion fact I want to use. So you're going to multiply the top across, and I get 2 pi. And you're going to multiply the bottom across, and I get 24 times 60 times 60. Now this is just going to give me the angular speed in radians per second. This isn't my answer. But like I said, everything has to be in radians, and our time is almost always going to have to be in seconds. So you're going to have your angular speed in radians per second if you're going to want this to work. So I don't know what this number is, and that part doesn't really matter because the next thing I have to do is I have to take this and then multiply by the radius. Now, the radius is 6.37 times 10 to the 6 meters. This might be another problem for some of us, which is why I wanted you to have your calculator with you, the calculator you're going to use on the test, because I'm afraid some of us have probably not been using the correct feature of your calculator for a number like this. And if you don't know what I'm talking about, you need to be able to use scientific notation with what we're going to do next. And if you're unfamiliar with it, I need you to look for the button on your calculator that says EE. On the TI, I believe you have to go up and hit the second function to get the EE. So find it on your calculator, please. And I'm not trying to be a jerk, but you've got to do 6.37, then hit that EE button, and then 6. That's how it works. Do not use the button that says this. Do not use that button. That's the anti-log button, and it does something in your calculator. It's a function. And if you use that, you can get mistakes. So the calculator doesn't function right that way. You want to use this because it actually treats all of this as one number. And so find that. And now you need to do all of that math, and then you need to multiply by this. Now, some of you have to be smarter than your calculator. And some of you just don't understand how the calculator works. If that's you, if you consistently get the wrong answer when you type it into your calculator, then use more paper. Okay? Type 2 pi and set it aside. And then type in your calculator 24 times 60 times 60 and write that down. Use more space on your paper and don't trust your calculator to do it all in the calculator. Because you've done it. You sat there at the table. There'll be 5 of you sitting around a table, all actually trying to calculate the same number, and all of you getting 5 different responses. This is why. It's because you don't understand your calculator. And we're not going to spend time to learn how to use your calculator. It's not important enough. But you guys should be getting that 463 meters per second now. And if you're still not, well, then we got some issues. But we should stop here just for a minute. We have to talk about the fact that this is 463 meters per second. Now, I want to get away from the whole using your calculator for a bit and talk about what this actually means, that when you're standing on the Earth, if you're at the equator, everybody at the equator is moving at 463 meters per second. This is why we launch rockets at the equator, because they're already moving that fast. To understand how fast that is, the speed of sound is 333 meters per second, which means everybody at the equator is traveling faster than the speed of sound. Every mountain at the equator, every bit of air, every person, every landmass is moving faster than the speed of sound. And all the air is too. If you want to know why we get hurricanes, just imagine that there's these huge mountains that are stirring the air by traveling at the speed of sound or faster. The edge of the earth travels that fast. Now, we are not on the equator. So you might think, well, we're not on the equator. So we're not traveling that fast. We're at latitude 40 degrees. So if you want to know how fast we're traveling, just type in the cosine of 40 degrees and you'll see how fast we're traveling here in Florida. It's not much different. It's still quite fast. Now, yes, we would be better off if we wanted to launch rockets by trying to get to the equator. But since our United States isn't at the equator, we launched from Florida, the lowest place on the most southern place we could get to. That's why we launch rockets there. And there's a big ocean there in case you have an accident. You can just drop it in the ocean. The Russians didn't have this advantage. This is part of the reason we made it to the moon and they didn't. Our rockets could be smaller. They had catastrophic failures with the size of their rockets because they had to launch them from the Cosmodrome, killing hundreds of people. Their accidents never became part of the popular the history of our planet because they kept it secret. They didn't want people to know until later, after the Soviet Union fell. More of the history became known that they had several catastrophic accidents. So, it's not minor, the speed that we have when we're at the equator. So what I'd like you to think about is standing at the equator makes you lighter than if you're standing, say, at the North Pole. Because remember, you're traveling at 463 meters per second to the side. And that means the downward force of gravity has to be greater than the normal force on you, or you can't travel in a circular path. The centripetal force rules still have to work here, that there must be an unbalanced force acting on you when you're standing at the equator. So when I consider standing at the equator, the net force has to equal MAC. I'm accelerating when I'm at the equator because I'm traveling in a circle. And even though we're at cosine 40 degrees, we still have a substantial difference in our weight. This is measurable. If you take a scale and set it down at the equator and you walk up to the North Pole, you will see that you appear lighter at the equator than the North Pole because there's less normal force on you at the equator because you're going around in a circle. If you consider that towards the center has to be positive, you can actually figure out how much lighter you are when you stand at the equator versus standing at the North Pole. Now, I don't want to finish this problem. I don't care what the number is. It's what I want you to think about. because this problem seems weird when it's asked of you on your homework. But when you think about the fact that you are traveling in a circle, anytime you're traveling in a circle, the forces on you have to be unbalanced. So even circles as big as going around the Earth are going to have this effect. All right. Last, we're going to talk about gravity twice this year. This is the first time we're really talking about gravity in a way that's not just an acceleration. Gravity as a force. Up until this point, we've always said that the force of gravity is weight. And we've just said it's mg. That's actually been a convenient myth and mistake. We've been saying that because we needed some way of telling you about gravity. And so we started out by telling you that gravity was an acceleration. And then after that, we told you that gravity was a weight. But if you think back to when we first introduced forces, the first thing I said is that gravity was a force of attraction between all objects with mass. That's how I describe gravity. So today I need to be more specific. Gravity is very much a force of attraction between all objects with mass. So any two objects in the universe will be pulled together due to this force of gravity. Although weight is how we experience gravity on the Earth, the force of gravity is calculated different. To calculate how much force there is between any two objects, you need each one of their masses you need how far apart they are, which I will almost always refer to as the separation distance. And then you have to multiply by a constant. This constant is capital G. And you're going to confuse this with little g. So don't. This is not the same thing. This is called the universal gravitational constant. Little g is the acceleration of gravity on the Earth. Big G is the universal gravitational constant. It's on your equation sheet. Find it, please. I want you to know where it is because you need it for the next test. It will not be given to you on the test, will not be written on the test. So you need your equation sheet. Your equation sheet comes in 2 pages. The first page has all the constants that you're supposed to have access to on the test. So look for the capital G. Did you find it? Highlight it. You're going to need it on the next test. It's a very small number. 6.67 times 10 to the negative 11th. So it is very small. And I want to make sure you understand that that's why gravity is considered the smallest of all the forces. But look at those units that it's got there. They're a mess, aren't they? You do see it's kind of just a bunch of stuff. But look at this. Look what's going on here. I have kilograms squared on the top, and I have meters squared on the bottom, and I have to cancel all of that out and be left with newtons. That's why the units for this are newtons meters squared per kilogram squared. It's to cancel out the kilograms and meters that you're using and give you something in newtons. All this number is a big conversion fact to convert your mass and your distance into a force. We believe this is the same everywhere in the universe. In fact, we're counting on it to be. So your first job, and it's not particularly terribly hard, but it's got a lot of big numbers in it, is I want you to calculate the force of gravity on you, between you and the Earth. But I don't want you to do it this way. I want you to do it the way that would allow you to calculate that force on any planet. So I want you to do this way. All right? So everybody's going to do this or it won't work. I need all of you to do it. So here we go. You need to know what your mass is. And since you probably don't know your mass in kilograms, I'll help you out. If you know your weight in pounds, divide by 2.2. That's your mass in kilograms. So I'm going to lie and say that mine's 100 kilograms. So the force of gravity on me is going to be the mass of the Earth times the mass of me times the separation distance. That's just the radius. Times g. That's what all of you need to do, but you need something, don't you? Rachel, what is it that we need?
The mass of the Earth.
Yeah. I know. It's weird, but I have all of these bits of useless information memorized. The mass of the Earth is 5.96 times 10 to the 24th kilograms. She's a big boy. So there you go. Take a few seconds and try this out. This is not about actually getting your number. This is about dealing with the fact that there's a whole lot of big numbers. And you have to be able to do your calculating stuff. So that's what I want this to be about. When you're done, give me a yes in the participant window because we have 2 minutes to be done. So you have to hurry. David, you're done? Okay. When you're done, you're going to do something that will allow you to know whether you're right or wrong. A lot of you might not know by looking at this number whether you're right or wrong. Got a few more coming in. So 3 out of 26. Got 7. I only got like 1 more minute before the bell's not going to ring. 12. When we reach the halfway point, we're going to move on. All right, we are there. Okay, if you want to know whether your number is right or not, divide by your mass. Take what you use for your mass and divide your number by the mass. If you've done it right, you'll get 9.8. That's how I know you're right. We already know how to calculate weight. It's your mass times 9.8. I wanted you to see if you could do this. So if your number, when you divide out by your mass, gives you 9.8, you did it right. If you divide by your mass and you don't get 9.8, you did it wrong. But that also should tell you something very important, something that's going to be on your next exam. That think about this, net force equals ma. If you want to know what the acceleration is, the acceleration of gravity on another planet, you use this formula to do so. That's what we just did. Think of it this way. What you just did was you took your mass, the mass of you, multiplied by the mass of the Earth, separation distance of the Earth, and g, and set it equal to the mass of you times a. To check, you wanted to see if this a was 9.8. What did you do? You divide it out by the mass of you. Which means that if you want to know what the acceleration of gravity is on another planet, that's how it's done. You set it equal to mg and divide out by the m's. This gives you the acceleration of gravity on the other planets. We'll play around a little bit with this on Monday, but this is really about it. Well, folks, you survived your first day of hurricane school. Hurricane school, I know, crazy stuff. But the superintendent told us that if we didn't do this, they were going to make us come to school a couple of days over Thanksgiving. I think it was a big lie, but you know, not about to sabotage our Thanksgiving break. So I'm glad you guys are all here today. I appreciate you being here, and you being here gives you extra credit today for showing up for our hurricane school. So I have a list of all the people that are here, and you're going to see a column put right into our grade book that's going to say Hurricane Day 1, and you're going to get a little bit extra credit added to your grade. Okay? So you guys have a fantastic day. Please go on to your second period class. I hope they have something meaningful planned for you there too, okay? Anna's asking if we're going to have our quiz tomorrow. We're going to go over homework started at the beginning of class tomorrow. Hopefully we have enough here to do. We have not done everything I want to do, and we'll see how it goes from there. If I feel like guys are ready and we're going to get a whole bunch of A's, I see no reason not to. If you're not ready and we're not going to get a whole bunch of A's, well, maybe we'll wait till Monday. Okay? All right, guys, have a fantastic day.
Mr. Shelton,
Yes?
I was wondering if we had to like join a Zoom for research.
No, I'm going to have my Zoom open for research. So if anybody needs help with homework or needs tutoring or something, I always open it every day for research, but you do not need to show up for research.
Okay.
The e-learners don't typically. Okay?
Thank you. Have a nice day.
You
Mr.
too. Bye-bye.
Shelton,
Yes.
I was late to class today, so I was just making sure that I'm here on the attendance.
Yes, you are. I'm actually not pulling the attendance from this. I'm pulling it from the participation list that Zoom
Okay.
makes for me. So you'll definitely show up, okay?
Okay, thank you.
You're welcome. Sophia, did you have a question?